So please help me welcome to the stage Peter Wittick from the University of Toronto.
Thank you. This is my first time in Las Vegas, and this city is known for gambling. And personally, I can't wait to go out gambling tonight. And when I start thinking about it, I realize that this city is very much like a gigantic quantum computer. It's probabilistic, and there are all sorts of things happening that we don't fully understand. So what I would like to do today is to motivate why quantum computing is interesting in the first place, why you should bother with it. Then I want to tell you how it works. And then I want to give you 2 building blocks that you can start using to create new learning algorithms. And finally, I want to give you very specific applications that you can start thinking about using the quantum computers we have today. So let's dive into it. Why quantum computing? Why do we need this thing? So there's a lot of interest in it. Many commercial companies started to build quantum computers. This includes major corporations and also a variety of startups. And the market is dominated by North American companies. And the oldest player in this field is D-Wave Systems, based out of British Columbia. They've been around for 19 years, and they've been building quantum computers for over a decade. Over these 19 years, they raised over $200 million. And last year, the Chinese government and a couple of Chinese companies indicated their interest. Alibaba committed $15 billion. So I really hope that Jeff Bezos is listening, because it is time for Amazon to catch up. So why do these companies want to build this thing? Why do they spend billions of dollars on it? There are fantastic things that you can do with quantum computers. You can think about creating or finding superconducting material that works at room temperature, which will revolutionize how we transmit energy. You can think about creating personalized drugs that account for your genetic makeup, that is tailored to you. And yes, you can mine Bitcoin faster with quantum computers. But this promised land is about 20 years away. So the quantum computers that we want are perfect and scalable and noise tolerant. And that's not where we are today. The quantum computers today are very imperfect. So the question is, what do we do with these quantum computers between today and 20 years from now? And this is where quantum machine learning becomes interesting. Think about the hardware that you already use in your machine learning setup. You use your CPUs, and what a CPU does is, say you have a learning algorithm, then you decompose it into elementary operations, additions, multiplications, and so on. And you execute these elementary operations either in a sequence or in a few cores. And GPUs do the same thing, but on thousands of cores. And this is what enabled deep learning, right? This is what enabled to create these very large neural networks. But GPUs use a lot of power. So there is a shift towards alternative architectures, like field programmable gate arrays, which are very good at real-time data processing and learning on signals, or application-specific integrated circuits, like these neuromorphic chips that Intel builds, or the tensor processing units that Google has been experimenting with. But it doesn't matter which one of these you look at. They are all digital circuits, which means that they do these elementary operations, and they are deterministic. So if you add 1 + 1, you always get 2. Now, add quantum computers to that. So what is it that quantum computers offer that you cannot do with digital hardware? First of all, quantum mechanics is not deterministic. It's probabilistic. You can create quantum algorithms which are deterministic, but those are very boring. You don't want to do that. And second, a quantum computation is global, which means it's very good at solving problems which cannot be decomposed into these elementary operations. So these are the two defining characteristics: probabilistic calculations and global calculations, calculations that should not be decomposed. Now, let's go back to digital architectures. We know that the state of the art is deep learning. It's all about supervised learning and discriminative problems. So these digital architectures are very good at telling things apart, whether that's about telling cats and dogs apart, or whether it's about telling which word comes next in a sentence when you do machine translation. And you're making advances in other problems, like unsupervised learning, where there is no a priori structure in your data, or generative learning, when you're trying to model an entire joint probability distribution. But these are difficult tasks to do with deep learning and traditional digital hardware. And the pitch for quantum machine learning is that you should not do these things on a $50 million quantum computer if you can do it on a GPU or on AWS. Rather, focus on the hard problems, unsupervised learning, and generative learning. And it's surprising, but it's true that there seems to be a fit between what our contemporary imperfect quantum computers can do and what is difficult to do in machine learning. Okay, so what is quantum computing? Now, think about a digital computer. What it does is you take a sequence of zeros and ones, a bit string, and you transform it into another bit string. And you can start from any bit string, and you can end up with any other bit string. So in this sense, your operations are universal. Now, it doesn't have to be this way. So you can also define a probability distribution over bit strings. So instead of directly manipulating individual bits in your bit string, now you are transforming probability distributions over bit strings to express what you want to do. So for instance, if you want to price a financial asset, that's one great example where you need this. Or certain scientific calculations need this kind of probabilistic calculations. But we don't have a hardware to do this. So what we do is we take our digital computers and fake random numbers to simulate these probabilistic transformations. Now, a quantum computer does exactly this very naturally. So a quantum computation is nothing but a transformation of a probability distribution into another one. But it's not an ordinary probability distribution. This is a quantum probability distribution, which means that you can exploit quantum effects like interference and entanglement. So you can pull out certain correlations in your system that are very hard to do classically. So let's take a second look at this part, because this is critically important. So again, let's think for a moment. On a digital computer, you take your elementary operations, additions, multiplications. And that's all you do. That's why you only need just 64 bits on a CPU, whether that's your phone, your workstation, or any node on AWS. It's the same thing, elementary operations. That's not what we want from a quantum computer. We want the quantum computer to have thousands and ideally hundreds of thousands of qubits. And the reason is because a quantum computation is global. It considers your entire problem at the same time. And this is how you exploit these quantum effects, like entanglement, which is a very strong form of correlation, to extract knowledge from different parts of this global problem. So think about a traveling salesman trying to visit a number of cities and trying to find the shortest route. So what you would do on a digital computer, you would evaluate all possible combinations, and there are exponentially many of them. And what a quantum computer would do, it would create a uniform distribution over all solutions, and it would transform this distribution into one which has a high probability over the optimal, the shortest way of visiting the cities. So that's, in that sense, it's a global calculation over this entire graph. And that's why we need so many qubits. OK, so now you know everything about quantum computing. So let's take a look at how we build a quantum computer. So when we talk about quantum computers, we actually talk about different paradigms. The first one generalizes digital computing. So in a digital computer, you can do this universal transformation. You can start with any bit string and end up with any other one. Now, in a quantum computer, this means that you can start with any quantum probability distribution, and you can transform it into any other one. Now, this requirement for universality is a major engineering challenge. So in this model, we have less than 100 qubits today, and we really want hundreds of thousands. So we have a long way to go. The second paradigm is called quantum annealing, which solves a lot more specific problem. It solves a binary optimization problem. And since this is more specific, the universality is not a requirement, and therefore it is easier to build. So in this paradigm, we are up to 2,000 qubits today. Again, we would like to have hundreds of thousands, but it will take a while to get there. And both of these paradigms are relevant for machine learning. So it's worth looking at both of them. And it doesn't matter which one you choose. Nobody actually agrees what's the best way to build these things. So there are a bunch of competing architectures to create quantum computers. The first one is the superconducting architecture. This is great because you use the exact same silicon fabrication that you use to create every single digital device that you have. The only difference is that you cool it down to near absolute zero, and that's it. And the second option is to use light, to use photons to encode information and do calculations. And the third major direction is to trap individual atoms in laser beams and let these trapped atoms interact, and this interaction is what creates the calculation. Today, nobody knows which one of these approaches is going to win. The most crowded market is the superconducting one, simply because it's just the easiest in the sense that you can use existing fabrication facilities. But there are companies and startups doing other paradigms as well, and we really, really don't know which one of these is going to give us the best, most scalable quantum computer in the long run. OK, so pick one. One thing that we are looking at is the number of qubits. We want a lot of them. But that's just part of the equation. Imagine that you are building a deep learning network, and you have a restriction. You can only use 10 lines of Python code. That's it. It would be very unnatural, right? So you don't expect that limitation. But that's exactly what happens on a quantum computer today. We would like to run very long algorithms on a quantum computer, but we cannot. And the reason is that your quantum computer interacts with the environment. And this interaction with the environment is uncontrolled. So the longer you run a quantum algorithm on the processor, the less and less it resembles the calculation you want it to be. So what we do is we do a short burst of calculation on the quantum hardware, extract the results, do some post-processing on a classical processor, then go back to the quantum hardware, tune some parameters, and we keep doing this iteratively. So short burst of calculation and lots of classical processing. This is this hybrid classical quantum paradigm, and this is going to dominate quantum computing at least for the next 5 years, but possibly for the next decade or so. All right. So let's take a look at what you can do with these imperfect, noisy quantum computers. The first building block that you can start thinking about using in machine learning is optimization. Any quantum computer out there can do optimization. So let's take a second look at this paradigm called quantum annealing. So what a quantum annealer does can be thought of as this. Imagine that you have two magnets. one would have north face pointing up. You can think of it as a 0. Then the next magnet is going to have south face pointing up because magnets like to anti-align. So you can encode this as a 1. Now you can have a whole sequence of them, and each pair will anti-align. Now, you can change the distance between individual pairs. So some magnets would interact more strongly, others would have a weak interaction. So to spice things up, you could add a large external magnetic field. So this magnetic field would flip some of the magnets that weakly interact, and some of the magnets which are strongly interacting between themselves would stay the same. And when you think about what it means, since you already encoded zeros and ones, this is like a binary optimization problem. And it turns out that if you think of the physics of it as magnets, nature actually finds it difficult to solve this problem and find the optimal configuration. It might get stuck in a local optimum. So there wouldn't be enough energy to flip certain suboptimal combinations of magnets. And looking at it as a computer scientist, this is an NP-hard problem. So there's this very natural correspondence between what's computationally hard and what's hard to do in a physical system. And this is where quantum mechanics offers a shortcut. Because what you can do is you can put all of these magnets into a uniform distribution, so you have a uniform distribution over all possible configurations they can take, and then you do this change, this transformational probability distribution, so it would peak over the optimal configuration. And then you look at it, you measure the system, you extract the solution, and ideally you get the optimal answer. And so this is what actually a quantum annealer does, but you can also do the same thing on a gate model quantum computer. Just by virtue of being universal, it can do anything that a quantum annealer can do. And for instance, one way of doing it is to mimic this transformation that the quantum annealer does in a discrete way by using gates and replicate the exact same outcome. Okay, so what do we do with this binary, this discrete optimization in machine learning? Like, you really, really shouldn't think about doing deep learning with this. Because in a deep learning network, you have billions of weights. And each of these weights are represented by 32-bit precision numbers. Now you have at most 2,000 qubits on a quantum computer today. So there is this misfit. You shouldn't optimize a deep learning network on a quantum computer. You have to think about machine learning problems that are quintessentially discrete. So one example is when you have a whole bunch of different deep learning networks that you already trained, and you want to combine them into one ensemble to create a stronger predictor that overcomes the limitations and the errors that the individual networks do. So this combination is discrete. So that's a very natural fit to do on a quantum computer. And the second one is to think of like unsupervised learning problems. So think about some large social network where you want to find clumps of similar people, for instance, for marketing purposes or to identifying terrorists. And this is a hard problem to do on a classical computer, but it's a very natural fit for a quantum computer and for optimization. Okay, so that was the first building block that you can start thinking about using in problems you are interested in. The second one is sampling. So quantum computing is probabilistic, which means that it allows you to pull out samples from a probability distribution cheaply. And I also told you that a quantum computer interacts with the environment in an uncontrolled fashion. And it turns out that we can actually exploit that. So instead of fighting this interaction, this uncontrolled interaction, we can use it as a resource. So think about a hot cup of coffee. If you remove the lid, then it will equilibrate with the environment, and eventually it will reach room temperature. So a quantum processor is exactly like this cup of coffee without the lid. It interacts with the environment and equilibrates. And if you start pulling out samples from the equilibrium distribution, you get a very specific distribution. You get a Boltzmann distribution. And this distribution is very difficult to mimic classically. To fake this Boltzmann distribution classically, you need to do lots of calculations. And this is exactly the distribution that you need to train this family of learning models called probabilistic graphical models. So think about Markov random fields. Think about Bayesian networks. Think about Boltzmann machines. So these architectures can do things the deep learning cannot. So in that sense, quantum computing is not about replacing or accelerating deep learning. It's more about offering something complementary to what you can already do with the state of the art. So think about the Markov random field, where you can have random variables, say corresponding to symptoms of patients. Some of these are observed. Some of you already made some observations on a patient. And then you can ask queries. What's the most likely disease that this person has? And if that's the most likely disease, then what are the other most likely symptoms that we should check? So these are questions that would be very difficult to answer with deep learning. And it's a very natural fit for these probabilistic models. So in this sense, we expect that quantum computers can do the same thing for this family of models than what GPUs did for deep learning. Quantum computers can really enable these models to scale up and be useful. And that's the tip of the iceberg. You can start thinking about good old-fashioned AI, where you had logical statements. If there are clouds, then there shall be rain. And you can start mixing them up with these probabilistic approaches, which account for uncertainty in your data. And it turns out that these models, for instance, Markov logic networks, already also require using samples from a Boltzmann distribution. And then you can take it even to the next level and think about probabilistic programming and how that would integrate with quantum computers. So there's a lot to explore here. So that's about the theory. So let's come back to planet Earth and look at the actual applications that we can do today. So in the University of Toronto, we have a bit of an experiment going on. It's under the umbrella of the Creative Destruction Lab. And we are running a startup incubator focusing on quantum machine learning and quantum software. We launched it slightly over a year ago. So we are into our second cohort. And in every cohort, we see over 20 companies trying to do interesting things with quantum computers we have access to today. And looking at now over 40 startups, we start to see some verticals emerging as being very natural fit to quantum computers. The first one is logistics. And when you think about it, it makes sense. I mean, you have these graphs describing locations and some distances between them. So it has this graph structure that quantum computers can exploit and give you some advantage. And you don't have to restrict your thinking just to vehicle routing and traveling salesman type problems. There's a lot more here. Think about scheduling flights, or think about automated warehouses where you have all these robots running around. And now you could optimize those routes by using quantum computers. Then the second big application area is drug discovery. So in this case, you combine machine learning with some optimization over molecular structures. So think about folding proteins. Folding proteins is a really hard problem classically. You can do maybe 15 amino acids or so on a classical supercomputer, and it takes about a week to solve. And 15 amino acids actually doesn't fit the quantum computers that we have today. But what you can do is have a coarse-grained description of the amino acids, embed that coarse-grained description on the quantum hardware, get the optimum of this coarse-grained architecture, and then bootstrap your classical calculations with this coarse-grained optimum. And if you do this, you reduce the overall calculations from 1 week to 1 day. So you can massively accelerate the discovery of interesting proteins, for instance, for creating new drugs that have fewer side effects than the tiny molecules that you would use in today's medicine. So this is already happening. There are 2 companies doing this. Then you can take that to the next level and look at the discovery of new materials. So in this case, it's very, very important to look at the quantum mechanical properties of these chemical compounds. And this is extremely difficult to do on a classical computer because the degrees of freedom of quantum mechanical system grow exponentially fast. So you really need a quantum computer to solve these problems. So think about light-emitting material. If you want to find new light-emitting material that has lower and lower energy consumption, then you need to look at their quantum mechanical properties and look for new compounds so that your phone's screen will consume half the energy and your battery will last a lot longer. So this is also happening. There's a company already doing this, a startup doing this. Then the last major application area is finance, where it's very natural that you have problems of the type of sampling and the type of optimization. So when it comes to assessing the risk of a certain asset that needs these probabilistic distributions and sampling these distributions, then you can think of portfolio optimization, which is essentially a discrete optimization problem. So it also maps very naturally to quantum computers. So my key takeaway is that quantum computers are here. They are imperfect, but there are at least 3 quantum computers out there that you can start accessing for free through a Python API. So this is the right time for you and your organization to start experimenting and see how you can integrate quantum computing in the products and services that you develop. Thank you.